everyone, welcome to week 6. We are starting our next chapter. We are going to be in unit 5, exponential functions. Again, I just want to let you know that there is a capstone for this, so when we do take our chapter test, one of those 3 capstones does fall with our exponential and log chapter. Okay, so where I am is on page 64 in your notes, and the other place I am is in the week 6 page for today. You will see a link that says Desmos regression or something like that, Desmos regression calculator, and you need to click on that link so you can get to this website, because this is a little bit faster than using our graphing calculator, and it's just much easier to use than our graphing calculator. And this is a particular app within Desmos that if you just went to a regular Desmos page, you would not find this. So you definitely have to click on that link. But otherwise, we're going to go ahead and get started. So in Algebra 1, you did learn about exponential functions, that you start with the beginning amount, and then things grow at a certain rate, at a certain percentage. So credit cards, you have an APR, that's a percentage. So that's an exponential problem. When you buy a house and you take out a loan and they charge you interest, that's a percentage. And so that, because it's a percentage, is an exponential function. So we're just going to spend a little bit of time just kind of reviewing some of those basics that we learned from Algebra 1. So in our first one, we have the population of a town. It's modeled by this, okay? And P is the number of people measured in thousands. So this isn't 100 people, this is 100,000, 110,000, etc. And T is the year since 2000. So this is the year 2000, 2003, 2005. So what we need to do is make a scatter plot of the data, run a linear regression and an exponential regression, and we're going to determine which fits the data better. So this is something you did do in Algebra 1, you did it on your graphing calculator, but I'm going to be switching to Desmos now. All right, and here we go. So what you need to do is you need to take the time, the years, 0, 1, 2, 3, 4, 5, and you're just going to change all of the X's. I do recommend that after you type a number in to hit the down arrow, don't hit the return button, and just put in your years. And then you do the same for your Y values. So, and the main thing is you just got to go slow so that you don't mistype anything, and that the left data point matches up with the right data point. So I'm just going through and typing these in. This is something I would expect you to be able to do without my assistance, especially since we're using Desmos. So again, I've typed in my numbers. I just want to make sure that everything's correct, because if your data is incorrect, then all the equations come back incorrect. All right, so they're there. And what I can do is I can try to find the points. Here they are. A really easy way to find the points is to go up to this wrench in the top right and go to where it says x-axis and y-axis, and just change those dimensions to the dimensions that you see in your table. So I see time going anywhere from 0 to 5. So I can make my x-axis just go from 0 to, maybe I'll just go a little bit higher than 5. I'll just do like 7. And then my y-axis, I need anywhere from 100 to 161. So maybe I'll just go a little lower, like 50, and then go a little higher, and I'll make it 200. All right, and then you can see the points. Now this is a little tough, so if you hit this arrow right here, it'll just move that in, but you can kind of see what that's looking like. And then because Desmos is so great, I can just kind of zoom out a little bit more without having to go back in. So when I'm looking at this, you know, it's kind of hard to tell, does it look linear or exponential? Whoops. So what we don't have to worry about is that decision. Does this look like a line, or does this look like an exponential curve? So what I can do is hit this, so let me show you what I just did. I hit this arrow back, and what I want to do is down here in red, green, and orange, they give me red for linear, they give me green for quadratic, which we don't need. So what I'm going to do is just hit this green circle. It's just going to take green out. Okay, you could also hit the X, because we're never going to use quadratic right now. And then the orange is our exponential. And what I want to do is, under the word parameters, is see that they are giving me values for M and for B that I can put in my equation. And then down here, they're giving me values for A and B that I can put in my equation. So what I'm going to do is write that down. on my paper, and we're going to record that equation and store it in Y1. So I don't want to write both of them. I only want to write one of them. And the way to figure out which one is the better one is you look at the R value. And you want to see if that R value is either close to 1 because your points are going uphill. I'm not sure which way uphill is when I'm making a video. Or you want R to be -1 because your points are going downhill. All right? So because these points are going uphill, I want for R to be as close to 1 as possible. 1 is perfect. So when I look at the red one, the R is 0.9976. So think of it as 99 cents. But when I look at the other one, the orange one, R is 1, which is perfect. Like, that never happens. So what I'm going to do is ignore the red. I can just tap on the red circle. And if you see, you can see that this curve is hitting every single point. So I'm going to take the equation, I'm going to write it down, and then I'll switch it back so you can see what I wrote down. So I'm just seeing, all right, so it's going to be P because they're using P, and then in for A, they give me 100, and then for B, they give me 1.1, and then I have T as my exponent. So let me switch back so you can see what I'm showing you. So this is my equation, all right? They had y equals, but we're using p instead. In for A, under parameters, they had 100. In for B, we will want to always put this number in parentheses. And then t is our exponent. Where they have x, we write t. Okay? So what I probably should have started is that, since this is exponential, I do just want to remind you of your exponential shapes. This is exponential growth. Kind of looks like a J maybe. And this is exponential decay. And we'll talk more about those, but right now we're just looking at the equation, deciding which one fits better, and then we're going to be using that equation. So according to your model, what is the population predicted in 2020? The next one, according to your model, when did the population reach this amount? And then we'll be finding the average rate of change. And there's a couple of ways we can do this. So first of all, I do want to realize that 2020, I wouldn't be putting 2020 in. I want to put in the year since 2020, so that means my time would actually be 20. And then on the next one, when did the population reach 350,000? I don't want to put 350,000 in. I want to put it in the format that they have, so I would just put 350. All right. And then this is just, from 0 to 5. So what's going to happen now is we're going to totally ignore this and only be using our equation to answer these 3 questions. And Desmos does it great. It's really easy to do this. So I'm going to switch back to the screen. And what I want you to see is that we're going to be doing the first problem where t is 20. So what I can do from there, all right, is if I want to start to work with some of the math, is I can hit this button here, all right, and just get a new calculator going, and I'm going to type in the equation that they want us to use. So 100, parentheses, 1.1. I'll make my exponent. Your exponent is, you can't see this, hold on. So down on the bottom left, I have a keyboard that's attached, and this a to the b is my exponent. So I could put in x, all right? And then again, if you can't see the equation, I'm just going to zoom out a little bit using the touch screen, and we're going to see this. All right? So this is the equation that's going to get me all my answers. So let's start with the first question. According to your model, what is the population predicted to be in 2020? So you got 2 options. One is you can just go to the x, turn it into 20, and it's going to give you the answer. And because it's people, we kind of want to think about what to round to. So certain things will round to the nearest whole number, but when in doubt, just go 3 numbers behind the decimal place. But since this is people, I'm going to take 672, and I'll just make it 673. All right? And I'm writing these answers down, and then we'll come back and look at them. So on the question that it says, what is the population predicted to be in 2020? I've got 673. All right. The next one I'm going to skip for now, and I'm going to go to what is the average rate of change in the population for 0 to 5. So this time I want to show you the other way you could have done this. I'm going to leave it as x, and I can go up here to this wheel, and then hit this table, and then I can put in the two t or x values and see what they want me to use. So for 0, I get 100, and for 5, I get this number. So I'm writing those coordinates down, 0, 100, and I'm also writing 5 with the 161.051. All right, and I'm going to come back to the paper. We'll actually do the math when you can see the paper. And then I want to answer the other question. So what I don't need is this table anymore. If I hit this x, then I have to retype the other equation, or the equation again. If you just hit this back arrow, it's going to, until we get back to where we are, that's great. So this is a systems of equations. So I am actually going to switch back for this quick moment. What I want to do is, if 350 is going in for P, and this is my equation, we've done this many times. And what we're going to do is put one of these, you could actually use your graphing calculator as well, into y1, and one of these into y2. And in Desmos, our y1s and y2s are just different boxes. So I could just tap a different box and type in 350. Now, Desmos works as a calculator and a graphing calculator on one screen. So if I just type in numbers, let me get rid of this 350, like 2 plus 4. Right now it's acting as a calculator. You can see the answer of 6. If I want it to act as a graphing calculator, then to tell it I want it to graph 350, I have to type in the equals y part. And I realize you can't see this, but I'm just going to zoom out a little bit more. And there I find my blue line crossing my red curve. And remember, I've shown you that you can just tap, and then you'll get where they meet. So that x value is, when did the population reach 350,000? That x value is my answer. So I'm going to write that down on my paper and then come back to the actual paper. All right, let me go back. So going to this question, my time would be this. I do want to label it. So in about 13 years, a little bit more than 13 years, that's when my population would reach 350,000. As far as this answer went, remember, I want it to match thousands of people, so I'll just add 3 zeros, and that's how many people are living in the city in 2020, 673,000. And now with this, I'm going to do the average rate of change formula, which we've seen so many times. It's where I'm going to subtract my y's on top. So I'm going to take the 161, and I'm going to subtract the 100. And that means I'll have to subtract my x's the same way. So I'll do 5 minus 0. And now I'm just using a regular calculator. But when I subtract these, I get the 61.051. In my denominator, I get 5. And I just want to divide those. So this I'm doing on the calculator. And when I'm done, I get 12.21. I'll write the whole thing down. It's not that long of a decimal. And now, what was the average rate of change? We do want to start explaining things. So what's happening here is, what's changing is your population. It's increasing. And they're telling you that they're looking at it based on years. So when you get an answer, and this is a change, it's the population that's changing. So this is how much the population is changing each year. Now again, I want to think of that the whole data is written in thousands. So if I just take that number times 1,000, this is what my population is going up by on average every year. So if I was going to put this in context, population, I'm going to abbreviate, is increasing. That's supposed to be increasing 12,210.2 people each year. Now, it's not always that exact amount. This is an average. So some months it might be more, some months it might be less. Okay? So again, the reason why I took this times 1,000 is because my data is in thousands, but what I'm working with is not thousands. So the other option is I could have changed this into 100,000 and made this 161,051 and then done the math, and I would have gotten straight to that. All right. So that's just a word problem. All right. Once you get the equation, you figure out which one you want to use, and then you start to put the numbers in. So now let's just talk about the basic shape of exponential functions. So just kind of summing up what this says is the most basic exponential function is f of x, like y equals b to the x. And this is just saying that b is any real number, but b has to be bigger than 0, and b cannot be 1. B is known as the growth factor. So when you were in Algebra 1, you saw this formula as b times g to the x. Now what we're doing is, first we're just ignoring this. We're using different letters, okay? So g in Algebra 1 was your growth factor, the number right next to the exponent, and right now we're using b, because b is the more traditional letter to use when you're talking about exponential. And so what we want is, again, this number has to be bigger than 0, and this number can never be 1. And we'll talk about that in a little bit. But the idea is I can now take these numbers, think of this as that parent function, and anything to a 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 8. But there's also a pattern that you learned about in Algebra 1, that this is the number that you multiply to get the next number. So if I start with 1, then I can multiply by 2 to get to 2, multiply by 2 again to get to 4, multiply by 2 again to get to 8. And then if I want the numbers on this side, instead of multiplying by 2, I would divide by 2. So 1 divided by 2 is a half. Take a half and break it in 2, that's a fourth. So you can get all these numbers. The other reason, just as a quick explanation why you would get a fraction here, is remember when you have a negative exponent, and negative exponent says to move this, and now with 2 to the first being in the denominator, it's 1/2. Or here, this says move it to the bottom, and then 2 to the second, that's why you get 1/4. So just a lot of Algebra 1 things coming back to us at once. So what I'm going to do is quickly graph this. So I start with 0, 1, 1, 2, 2, 4, and 3, 8. And then just so you can see the full shape, I'm going to estimate these points. They're not easy to graph, but I can still, we'll survive. All right, so there's the half, there's maybe a fourth, maybe not quite like that. And the shape looks like this. And what hopefully maybe you remember or you don't remember is there's like this invisible wall there. It's called an asymptote. I'm going to highlight that word for you in just a moment. And it's saying that this shape for now cannot cross this wall. Okay, it can't touch the wall, it can't cross the wall. They all have a horizontal asymptote at y equals 0. And another good way to see that is if I just put this function into my calculator, the bell's going to ring here in just a moment, and I look at the table, you're going to see that as x gets smaller and smaller, my y's are getting smaller, but they're not becoming numbers. This just means it's 6.1 times 10 to the -5th, which means I'd move my decimal 5 times to the left. So when you're seeing E in a calculator, that means you're seeing 0 pretty much. So these numbers are close to 0, but they're never getting to 0, and they're never becoming negatives because I don't see any negative numbers in front. So, all right, let's take a look at the next one. So this is exponential growth. And what you're about to see here is exponential decay. And we'll talk about, well, when do you know if it's growth or when do you know if it's decay? So again, anything to a 0 power is 1. A half to the first power is a half. A half to the second power just means 1/2 times 1/2, which is a fourth. And this is a half multiplied 3 times, which is 1/8. And if you think about, how do we go from 1 to a half to 1/4? You're dividing by 2 this way, which means you multiply by 2 this way. And again, the reason why this would happen is if I do have 2 to the, 1/2, bad writing, to the -1 power, the negative says you flip them, and then it's just 2 to the first power, which is 2. So remember, negative exponents just switches things around. Once you switch it, you can drop the negative and follow the exponent as normal. So here's -2 to the and 4, -1 and 2, there's 0, 1, there's the half, there's the fourth. So this is exponential decay. And again, we've got this wall, this horizontal asymptote that's just going along right here. Okay? And how do you know if it's growth or decay? So one last thing before hopefully the bell rings is, as I told you in Algebra 1, you learned that the number right in front of the exponent is called the growth factor. And the growth factor is what you multiply by to get from one number to the next in a table. So this says I should be multiplying by 2, and this says I should be multiplying by half. So when I multiply by 2 over and over again, you're going to see the numbers getting bigger. And when you multiply by a fraction, like a half, you're going to see the numbers start to get down. So first lesson here is you know it's going to be exponential growth if your b is bigger than 1. So multiplying by 2, things get bigger. Multiplying by 3, things get bigger. Multiply by 4.5, things get bigger. You're going to notice that it's decayed this shape if your b is in between 0 and 1. So you're taking half of something. You're taking a third of it, a fourth of it. When you do that, your amounts become smaller. And the reason why it can never be 1, okay, is if I do go to my y equals and I just take 1 to the x power, then hopefully you realize that 1 to the third power is 1. 1 to the fifth power, 1, 1, 1, 1, 1 is 1. And so if I have that, all my y values stay the same, and then when I graph them, I actually just get a flat line. I don't get an exponential curve, okay? So that is our first page of notes, page 64. The bell has rung, so I'm going to stop the video, and we'll probably just have another video following this. It'll be a playlist, maybe. I don't know.